We've been talking a lot about reactions of aldehydes and ketones, but we haven't really said too much about how to make them. So many simple ketones and aldehydes can be purchased, but more complicated aldehydes and ketones require reactions for their formation. Luckily, alcohols are useful functional groups for the formation of ketones from secondary alcohols or aldehydes from primary alcohols. And this process occurs via oxidation, which is the opposite of reduction. And so oxidations normally occur by taking a primary or secondary alcohol with a metal. So let's draw out a generic mechanism right here. And so if we have an alcohol, let's say this primary alcohol, and we react this primary alcohol with a metal at a high oxidation state. Well, so let's say M plus X. Okay. What happens is that the oxygen will basically attack the metal, and so we get a system in which we've got now a new oxygen metal bond, all right, and this is a oxidation state plus X. All right, we get a positive charge on oxygen. What then happens is we lose a proton. And these are reversible in these two steps. We lose a proton to generate a neutral species. And then what happens is that normally some base comes along and does a deprotonation. So we have a hydrogen atom right here, and this base can deprotonate, form a new pi bond, and then the two electrons from the oxygen metal bond will go up onto the metal and reduce the metal. And so the net result is that we have, in this case, an aldehyde, a doubly bonded oxygen, plus a metal in now the plus X minus 2 oxidation state, because now we have reduced metal. And so this is what happens in a generic alcohol oxidation. Now, there are really two transformations that are really important here, and so let's talk about those. The first one is the Jones oxidation, and in a Jones oxidation, what we do is we take an aldehyde, a primary or secondary alcohol. Let's take a secondary alcohol in this case, and we react it with the Jones reagent. So the Jones reagent is a chromium trioxide, aqueous sulfuric acid, and acetone. And the net result of this transformation is that we get the oxidation of the secondary alcohol to a ketone. All right, so how does it work? Well, the first thing that happens is we're going to protonate the chromium trioxide with a proton. So chromium trioxide is going to become protonated from the sulfuric acid, and now we have a metal center that looks like that. We're going to get the oxygen lone pairs attack the chromium, and then the electrons are going to move up onto chromium as a lone pair, onto oxygen as a lone pair. And so we have this intermediate. And this is then going to lose a proton. And then we don't have any base in this reaction, but this this species is known as the Chromate Ester, and the Chromate Ester is the chromium is pulling electron density so hard here that a base is really not necessary. Right, so electron density is pulled by the chromium, so no base is necessary. And so what happens is that the proton that's at that position falls off. And so we get a loss of a proton, and that proton is going to come off from that position right there. And so we lose that proton And the electrons are going to move up onto chromium as a lone pair. Essentially, you can eliminate water here. And so minus a proton gives you, in this case, the ketone, plus chromium oxide, so chromium 4 oxide plus water. Okay, and then that chromium 4 oxide is going to split into chromium 3 and chromium 5. And so chromium 4 is unstable, and so it actually splits into chromium 3 and chromium 5. And so this is the Jones oxidation. You've got chromium trioxide is protonated. You get alcohol to attack the chromium, forms a chromate ester, and then because the chromium is pulling electron density so hard via those oxygens, you don't need a base to deprotonate. It simply falls off to give you the new carbon-oxygen double bond. Okay, now while secondary alcohols react with the Jones reagent to give ketones, primary alcohols react to give carboxylic acids. So why not just give aldehydes? So let's talk that right now. And so let's start with this alcohol here. This is benzyl alcohol. And we're going to treat benzyl alcohol with the Jones reagent. So again, chromium trioxide, aqueous, sulfuric acid, and acetone. And the net result of that is the carboxylic acid. So why not the aldehyde? All right. So I'm going to skip ahead to this mechanism, because what we can draw for that's similar to the oxidation of secondary alcohols is that you will proceed through an aldehyde intermediate. Right, so we do get oxidation here, and I'll just say it's the same as the before. And so we get the aldehyde intermediate. But why does it not stop at the aldehyde? Well, the reason is that we're in the presence of aqueous acid. And so what we can get is a gemdiol intermediate. And so in the presence of aqueous acid, we're going to have a proton source around so that we can generate that gemdiol. So let's draw that out. So we get a protonated aldehyde here, which then gets attacked by water. So water attacks, and then we get a protonated gemdiol intermediate. With loss of a proton, we get the gemdiol. Now, it's the gemdiol that then reacts with the chromium. And so this is where you get formation of your carboxylic acid. Because at this point, we can take the chromium trioxide that's been protonated and react it with one of those two alcohols. So let's say we react it with this alcohol here. We're going to generate this intermediate. We get loss of a proton, again, to give a neutral species, to give you that chromate ester. And now, of course, we've got lots of electron density being pulled through that chromium into the oxygens, and so strongly that we get loss of a proton without need for a base. And in the process, loss of that proton leads to formation of a carboxylic acid. Right, so the reaction first forms the aldehyde, very similar mechanism to the oxidation of secondary alcohol. But because water and acid are present in the reaction, a gemdiol can form, which is susceptible to further oxidation. And so in the case of primary alcohols, we don't just stop at the aldehyde. We continue to oxidize into the carboxylic acid. Now, one of the problems with the Jones reaction is that it generates toxic byproducts, these toxic chromium species. And it also over-oxidizes primary alcohols. So there are several other reagents that have been developed to sort of circumvent these two problems. So the next reaction is the Swern oxidation. And this doesn't use chromium reagents anymore, but it still results in an oxidation. It still kind of uses a metal at a high oxidation state, although we're using the term metal a little bit liberally. Okay, so the Swern oxidation involves the conversion of primary or secondary alcohols to the aldehyde or ketone without overoxidation. And the reagents for this are something known as oxalochloride, DMSO, or dimethyl sulfoxide, and triethylamine. And again, the formation of, in this case, a ketone results from the secondary alcohol. All right, so what's the mechanism of this reaction? Well, the first thing we need to do is we need to generate the reactive oxidant. All right, so the first thing that has to happen is we take DMSO, and DMSO, of course, looks like this. But we can also draw it in its other resonance forms. We can take the electrons from that sulfur-oxygen bond and move it up onto oxygen as a lone pair. And so what we're going to have is a negative charge on oxygen, positive charge on sulfur. That is then going to react with your oxalochloride. So the oxygen atom is going to attack the carbonyl of the oxalochloride, and what you're going to get is a species that looks like this. So we've got a new carbon-sulfur bond. Excuse me, an oxygen-carbon bond. And you've got this tetrahedral intermediate here. What happens next is that the oxygen lone pairs come down, form a double bond, and we get loss of, this case, a leaving group, chloride. And so now we have this intermediate that looks like this. In which we've got positive charge on sulfur. And so that chloride that left in that step then can come back and do an SN2 reaction, so basically attacking that sigma star sulfur oxygen. What happens next is that the oxygen-sulfur bond breaks, forms a carbon-oxygen double bond. We get the carbon-carbon bond breaking and forming a lone pair up onto carbon, and then we've got loss of chloride at the same time. And so the net result of these arrows is that we have the oxidant that we're going to use in the next step. We have CO2 forming, CO forming, and chloride anion also forming. Okay, so it's this oxidant right here which is going to then react with our secondary alcohol. Right, so we did all those steps just to get to this oxidant. So then what happens is the alcohol reacts with the sulfur reagent. And we can kind of think of this sulfur reagent as being a metal in a high oxidation state. Right? We normally don't think of sulfur as having multiple bonds to it, but it indeed can. And so we get oxygen to displace chloride. Like this. We can get then deprotonation happening. Let's say we have chloride coming along. It can do the deprotonation to give us a neutral species at oxygen. Sulfur is still formal positive. Okay, and then what happens is we've got a labile proton here, and so triethylamine can come along, and it's a base, and it can do the deprotonation. So it deprotonates the oxygen, the carbon-hydrogen bond moves up to form a carbon-oxygen double bond, and then the oxygen-sulfur bond can break and form a lone pair up onto sulfur. So essentially what we're doing is we're reducing the sulfur. And so we get, as a product of this reaction, the ketone plus dimethyl sulfide. Right, and so this is a byproduct of the reaction, and of course dimethyl sulfide has a stench, and so you don't want to do this reaction outside of a fume hood. And so this is an alternative to the Jones oxidation, in which you can take primary or secondary alcohols and make the aldehyde and ketone respectively. There's one more reaction that we need to talk about, and that's the Pyridinium Chlorochromate oxidation, or something known as the Pcc oxidation. Okay, so PCC is a reagent that is an anhydrous form of the Jones reagent. And so pyridinium chlorochromate looks like this. Right, so PC stands for pyridinium chlorochromate. Right, so PCC. And it's an anhydrous form of the Jones reagent. So how does this react to give us aldehydes or ketones? What happens is that the Jones reagent can actually form in situ. And so by taking the electrons on oxygen and forming chromic acid, chromium trioxide, in situ, in this particular instance, there's no water around. Right? So because there's no water around, there's no chance that you can get the gem diol to form. And so what we can do is we can take primary alcohols, we can react them with PCC, and what we can get are the aldehydes. Okay, and so since this aldehyde is stable under the conditions, there's no water and there's no proton source, there's no strong acid, the aldehyde is completely stable here. It will not oxidize further to the carboxylic acid. So pyridinium chlorochromate is an anhydrous form of the Jones reagent. And anhydrous just means no water. And so because there's no water around, we can use primary alcohols, and we don't have over-oxidation to the carboxylic acid.